OWASP is a nonprofit that stands for the Open Web Application Security Project. OWASP is a community of developers, technologists, and evangelists improving the security of software through tools and resources. OWASP has 100 plus active projects, and new project applications are submitted weekly. Projects are open source and are built by our community of volunteers, people just like you. Community and networking. There are hundreds of local chapters worldwide and thousands of members. Meetings are free and open to everyone. They include training, talks, and networking opportunities. Education and training. OWASP hosts many events each year. They are a great way to improve your skills, build your professional network, and learn about new trends in the industry. One of the many ways you can get involved is to become a member. The membership benefits include discounts for events and trainings, your own OWASP email address and Google Workspace access, a vote in our OWASP Global Board elections. And recently, OWASP added a brand new member benefit, access to hands-on application security training through the OWASP Secure Flag Open Platform. Join us and become a member today.
Sorry about that. So thank you everyone for joining me. So and thank you, Cassio, for introducing me and inviting me. Sorry to make you read that long list of accomplishments. I'll make it shorter next time. So I think that one thing I should make sure to mention is that I only started at Facebook AI Research this month, and I was at Microsoft Research for 22 years, as Cassio said. So everything that I'm talking about here is kind of publicly known information that has, there's no restrictions on any of this information because this is all public content. So this is nothing Microsoft confidential and nothing Facebook confidential. Obviously, I just arrived at Facebook. So I just wanted to clarify that I'm only talking about all aspects of my work which are already publicly known and available. So I don't know exactly the audience here and how much you are familiar already with the topic I'm going to talk about. So I'll kind of zoom through my introduction. I don't see the chat, but if you do put questions in the chat, and if Cassio or Edmund, you want to speak up and read out any questions that come up, please just interrupt me, because I won't see the chat while I'm talking. Thank you. So I'm talking about private AI today. Private AI is a term that my team coined when I was at Microsoft Research. And it refers to a particular set of techniques that address a certain problem. So what is a potential privacy problem with artificial intelligence, or AI as it's being used today? These days, artificial intelligence is often used to refer to using machine learning algorithms, so kind of mathematically based algorithms, to make useful kind of predictions, classifications, recommendations. But in order to do that, typically you input your data in order to get some kind of recommendation. But in addition, if you think about it, the way that the algorithms are actually trained in order to make some kind of prediction or useful, classification or recommendation, is a lot of data, has been collected, and who knows from what sources, depending on who's doing the collection of the data. And that data has been used to train algorithms according to some, mathematical recipes. So in both stages, both in the training of models that can be used and also in the active, prediction, stage, data is being collected, which is potentially, sensitive data. So when I say sensitive data, I think about especially health data and financial data, but it could be things like location data, like your phone collecting your location, where you are every instant of the day. It could also be things like, genomic data. Genomic data contains a wealth of information about a person. So there's a lot of different types of data that you may or may not be concerned about how it is stored and used by others in the future. And so that's kind of the privacy problem in AI today, is all this data being collected, and how is it going to be safely stored, accessed, used, et cetera. So typical AI services today are hosted in the cloud and are often run by some kind of smart agent, for example, on your phone, such as Siri or Alexa. And so I got interested actually more than 10 years ago, especially in health and protecting health privacy. And around that time, there was a new mathematical tool that came, that had been an open problem for a number of decades, and a new solution was proposed around 2009. And this is a tool called Homomorphic Encryption. And what it does is it allows you to encrypt data in a way that you can still compute on it. So what that enables is that when you, if for example, you want to create a private version of some service, a recommendation service, even something like a health fitness app. Let's say you want to create a private version of a health fitness app so that all your location data from your fitness app would be uploaded to the cloud, not in the clear, but only in encrypted form. But you'd still be able to, get an analysis of your workouts and things like that. So what you need to enable such a kind of private AI service would be to be able to compute on that encrypted data without decrypting it. So that's what I'm going to be talking about for the next few slides. And I'll tell my goal in this talk is to kind of explain to you what homomorphic encryption is, kind of what is the state of the art in terms of what we can do in terms of AI and ML algorithms on homomorphically encrypted data, and also tell you a little bit about the community and developer communities, how much progress has been made on homomorphic encryption and what are the tools that are available today for you to use. So I like to explain homomorphic encryption in two different ways. This one is more just to kind of for entertainment purposes and to see if anyone's listening. So one way to explain homomorphic encryption is what I've been tagged as saying, I've created the name homomorphic encryption. So here we have Homer Simpson. And think of Homer Simpson as a jeweler. And you have a task that you want to perform, which is that you want to have some jewelry made from some gold that you have, and Homer Simpson is the jeweler. So now you have kind of a quandary, which is, should I trust Homer Simpson with my gold? He's looking a little shady here. And so what are we going to do? Here's a possible solution. You put your gold in a locked box and you lock it and you keep the key. And then you give Homer Simpson this awkward looking box here that you see on the right, where he can't really unlock the box because he doesn't have the key, and he can't really access the gold except through working on, with these gloves. And maybe that's why he's looking kind of unhappy, because he has to use these gloves to work on the gold in this glove box. But anyway, he's going to get the job done and then give it back to us. And when we get it back, since we have the key, we're going to unlock the box and take out the gold. So the idea of using this analogy to explain homomorphic encryption is that homomorphic encryption is like the locked box. You're taking your private sensitive information, which is the gold, and you're locking it by encrypting it, and then you're going to only allow the cloud provider, who's the analog of Homer Simpson here, or whatever service it is that's storing or accessing the information, you're going to only allow them to access the encrypted version of it, so they can operate on it and they can, manipulate it. But in the end, they're not going to learn anything from it, because the output is still going to be encrypted, and they will give it back to you, and you will decrypt it with your keys that you keep locally. So that's kind of the idea of explaining homomorphic encryption this way, and that is kind of the functionality of it, what it allows you to do. So it allows you to operate on encrypted data. So another way to explain it is more of a mathematical diagram here, and that is that homomorphic encryption is a technique so that you can take two pieces of information, let's just call them A and B, and you can operate on them, and you should be able to actually do any circuits, perform any kind of computation on the data. So that means and or circuits, which we can represent by two different operations. They're often represented as a plus and a multiplication. So if you can do two different operations corresponding to the circuits and or, then you'll be able to evaluate circuits on data. And the idea of homomorphic encryption, which is explained by this diagram, is that it's the property that it has is that you can switch the order of encrypting and computing, and you'll still get the same thing when you decrypt. So if you start up in the upper left-hand corner and you have two pieces of data, A and B, and you compute on it like you perform some operation like plus or multiplication, you're going across the arrow across the top, and then you could encrypt that data. So that would be, for example, the encryption of the product of two pieces of information. And this kind of commutative diagram is supposed to say that if you go around the diagram the other way, that is, you start by going down and you encrypt the data separately first. So you have two pieces of encrypted data, E of A and E of B, and then you compute on it, that, for example, multiplying the two ciphertexts together, that the ciphertext that you get should end up decrypting to the same thing, so that when you give the output back to the user, they'll be able to decrypt it, and the thing will make sense. So just to contrast this with normal encryption, if any of you use a normal, like for example, a U.S. government standardized block cipher such as AES, AES encryption is very robust. You can encrypt pieces of data, can encrypt A separately and from B, but then the ciphertext that you get cannot be combined. If you combine them, it'll just be nonsense. There's no meaningful way to combine, AES encrypted data. So that should hopefully contrast it for you with the status quo. And that being said, I think an important comment here is that AES is the U.S. government standardized block cipher. It was standardized in a NIST competition sometime around 2005, maybe a little earlier, a worldwide competition led by NIST, the National Institutes of Standards and Technology, which is a US-based agency, but teams from around the world, made proposals and attacked all of the submissions and stuff. And so that was a very well standardized process. And then on top of the standardization of AES, then there's lots of other kind of protocols and regulations that specify the use of AES in practice. And so for compliance reasons, you may see requirements, you have to use AES with this particular cipher suite or whatever. But homomorphic encryption is a relatively new technique which has not been fully standardized yet. And so we don't have the same kind of regulatory guidance built up around homomorphic encryption that will allow you to say, I'm just going to use homomorphic encryption and I'm going to check my compliance box. So that's one of the kind of challenges of this technique I'm talking about today, homomorphic encryption, although it's very powerful and very valuable. Just so you know, status quo is it's not going to allow you to check particular, compliance boxes because it's very early on in the standardization process. And I'll come back to standardization a little bit later. So let me just give you a little bit idea of the timeline. So like I said, homomorphic encryption, just the existence of a solution for this kind of open problem, homomorphic encryption, was first proposed really in around 2009 by Craig Gentry. And there had already been for many years encryption schemes that could handle like one operation. So for example, even RSA encryption, you can do, addition of ciphertexts. So it actually corresponds to multiplication of ciphertext, but it's addition of plain text. And so that's one operation that you can use. So there was already like PIA encryption, which has been standardized by ISO that could do one operation. But starting in 2009, the existence of a solution that could actually allow you to compute general circuits on encrypted data was proposed by Craig Gentry, but was considered very impractical, not implemented or implementable, and also not really based on hard mathematical problems that we were familiar with or had studied for a long time. So in 2011, there were several surprise breakthroughs coming from my team at Microsoft Research at the time. So a new encryption scheme proposed by a researcher in my group, Vinod Vaikunathan, along with Svika Brakersky, kind of put homomorphic encryption on a firm mathematical foundation. So creating a scheme which was connected to well-known hard lattice problems. And then in collaboration with me and Michael Narig in my group, Vinod and Michael and I came up with a lot of practical improvements, which allowed us to start really doing practical computation on ciphertext. And the main contribution there was a practical encoding scheme that allowed you to kind of encode, for example, floating point numbers as single ciphertext and allow for statistical computation, for example, with very low depth circuits that made a huge difference to the practicality because you didn't then need deep circuits to evaluate the kind of computation that you might want to do on encrypted data. So one other data point I'm going to mention in the history here, which was another kind of turning point, which is in 2016, along with researchers on my team at Microsoft Research, we proposed CryptoNets, which was the first demonstration that you could evaluate deep neural net predictions on encrypted data. And later, I'll show you a bunch of follow-up work that's been done by many teams around the world to improve this kind of thing. So kind of, if I were to, spoil the punchline at the end, there's enough work that has been done that really shows the viability of doing homomorphic computation on encrypted data for the purpose of deep neural nets and all kinds of other machine learning algorithms. So I wasn't sure how much to go into the high-level idea of the encryption scheme. I was wondering, Cassio, could you tell me in terms of a time check, like how much time should I spend talking versus leaving time for questions?
You talk as long as you want. I mean, until 1, we have the Zoom. And yeah, questions, I don't know if you prefer them to come as, we say them as they come, or if you prefer at the end, but we can do either way.
Yeah, so maybe, I don't know if you have a way to do a poll or raise hands if anybody wants to hear about the mathematics of how you how you do this kind of encryption. I could skip this and come back to it at the end, or I can go over it quickly. Any input for me here?
You guys can actually put messages in chat if you want, or one way we can do a quick poll is just use the participant reaction. So if you want to see the reaction, the mathematics behind homomorphic encryption, you can give thumbs up. So there's one hand from Bill. Another one from me. Daniel.
Okay, so excellent. So there's at least a few people that would like to hear a little bit about the mathematics. I'll just try to do it in a few minutes, and then we can come back to it at the end if anyone wants to ask questions. So I think it's kind of nice to explain how the solutions for homomorphic encryption work without using any notation. So I'm not going to give you any formulas or give you anything other than this slide, the words you see on this slide. And that's because different people in different fields always use different notation, and I find notation is a real barrier for understanding. But mathematically, I mean, the way mathematical-based crypto systems work is there's some hard mathematical problem that's used as the foundation for making something secure. Usually going along the lines of, okay, we're going to do some kind of a mathematical operation, like in RSA, it's just exponentiating some number, to some power, and that's a process which is hard to invert if you don't know how to factor, the modulus. Well, here, this is going to be based on lattice-based encryption, and the hard problem is to really find, short vectors in a lattice. That's kind of the hard mathematical problem. That's analogous to, for RSA, the hard mathematical problem is factoring large numbers that are product of two roughly equal sized primes. So here, first of all, what is a lattice? So I have some kind of pictures at the end, but what you should think of it as basically some discrete linear subspace of Euclidean space. So think of in small dimensions like three dimensions, just think of continuous space, and then think of a bunch of dots in that space, and those make up the lattice. And a lattice has the property that if you kind of add two dots together, think of them as being vectors connected to the origin. One of the dots is the origin. If you add them together, you should be able to get another, vector in the lattice. That's what it means to say it's a linear subspace. And so it's a discrete linear subspace, meaning it's like just the little dots are, distinct from each other. But an important point is that you can represent the elements in the lattice as a vector. And also, we're going to do this in very high dimensions. We don't do it in 3 dimensions. We do it in at least 1,000 dimensions. So the smallest lattices that we use for homomorphic encryption are dimension 1024. And for very complicated tasks like deep learning, we use much bigger size lattices. And it's always, we've been using only a power of 2 dimension lattices. And so instead of 1024 dimensional, we'll use roughly 32,000 or 64,000 dimensional lattices. So that means each element in the lattice is given by coordinates, which are, have, for example, 1024 entries. That would be the smallest. So you can see that the vectors are rather large here. And so here's how encryption works. So what you do is you've got a bunch of vectors. One of them is your secret. So that's your secret vector. And then other vectors are generated that are just random. So you basically generate all the entries of the vector randomly. And in order to encrypt a message, the message will also be encoded as a vector. And so what you do is encryption will just add to that message vector. It will add what we call a secret inner product. So that's taking the inner product of your secret vector with some random vector. So the ciphertext will give you the random vector, and it'll give you the message basically blinded by this secret inner product, which is your secret taking the inner product with the randomness. And so if you want to decrypt and you actually have the secret, and you know the randomness because it comes along in the ciphertext, you just compute the secret inner product and then subtract it from what you receive, and you'll get the message. Now, if I only did that, this system would be vulnerable to being cracked by just using linear algebra, by taking a bunch of samples and doing linear algebra. So instead, what we do is every time you do this blinding by a secret inner product, you also add some noise. And so what happens is that in the decryption process, if you know the secret, you can subtract the secret inner product, and then the noise is just very easy to cancel. It's just a small amount of noise on your message. But if you don't know the secret inner product, then it becomes a hard problem to decode these noisy vectors. It's basically a closest vector problem, like finding the closest vector in this lattice. And that's a fairly well-known hard lattice problem that has been around at least since the 1980s and has been studied. And the reason I mention the timeline here is because it's important for crypto systems that are based on mathematics, that the hard underlying mathematical problems be fairly well understood, and that we've had a chance to kind of attack them. There's a whole community of basically computational number theorists, which is my background, who work on attacking and finding the best possible algorithms to attack mathematical crypto systems. And so even though the ring learning with errors problem that's used as the foundation for all the current homomorphic encryption schemes was only kind of proposed, and the scheme was designed about 10 years ago, as I said, the BV11 scheme, the problems itself that it's related to, the hard lattice problems, go back to the 1980s. So I'd like to make two other comments about these lattice systems at this point. One is that the coefficients of these vectors can be viewed as the coefficients of the entries of the vector can be viewed as the coefficients of polynomials. So in practice, when we're implementing these schemes, like if you go into the libraries I'll tell you about later, it's all about multiplying together very high degree polynomials. So it's kind of efficient polynomial arithmetic that we're using to make these crypto systems fast. And then the second, so what goes along with that, polynomials are the ciphertexts, and as you probably know, polynomials can be added and multiplied together. So that's where you're getting the homomorphic properties from, is that you're taking data, you're encoding it as these vectors or polynomials, and you have to do that encoding process in a way that preserves the structure of the message. And then once you've done that, you can operate on these polynomials, and it will make sense. It corresponds to operating on the underlying data. And so that's where you get the homomorphic properties from, that you can add and multiply ciphertext together. And so what you might be able to see from that description is that encoding process is also very important. How do you take real data, like for example, floating point data, or data that would be used in some kind of machine learning algorithm, and how do you encode these messages as actual polynomials in a way that preserves the structure, but yet makes things as efficient as possible. So a lot of the research over the last 10 years has actually gone into that side of the question. So the other kind of high-level comments I wanted to make here is that these systems are currently considered what's called post-quantum secure. So there's an ongoing NIST post-quantum cryptography competition worldwide. It's roughly a 5-year process, started roughly in 2017. And to select new crypto systems that are not vulnerable to polynomial time attacks by a quantum computer once a quantum computer is built at scale. And that when I say not vulnerable, that means not known to be currently vulnerable to a polynomial time attack. It doesn't mean that somebody won't find a polynomial time attack in the future. But today, these lattice-based systems are post-quantum secure in the sense that we don't know polynomial time attacks. So homomorphic encryption is also attractive from that point of view, that these systems, once put in place, would be considered post-quantum systems. So I'd like to take a few minutes to talk about the work that my team at Microsoft Research did over the last 10 years. So I put together a team of researchers and engineers who had the goal of building a robust, usable homomorphic encryption library. And we call this Simple Encrypted Arithmetic Library. It was called SEAL. And it's available for download. You can go to sealcrypto.org, and I also have the direct GitHub link later in the slides. And SEAL was actually motivated by working and talking with people in the privacy community in bioinformatics, and who were interested in having some tools that they could use to protect sensitive, medical data, which was being collected or used in studies, funded by NIH, for example. So we wanted to make a tool that would be usable by essentially non-cryptographers, other developers and scientists. And so we developed SEAL and released it publicly for the first time in 2015, so almost 6 years ago. And since then, it's been widely adopted by teams around the world. And at the end of my slides, I have some links for other packages that have been built on top of SEAL. We actually released SEAL open source in 2018, and so it can be used, commercially for any purpose. And another thing that I have spent a lot of time on is working on building up a worldwide standardization community for homomorphic encryption. And we started that process in 2017, so about 4 years ago, and our community has hundreds of researchers and developers in it, including a lot of representatives from industry worldwide. And we released a standard which our community approved, which includes recommended parameters for safe use of homomorphic encryption schemes. We released that in November 2018, and it's been widely referred to by other kind of government agency documents around the world as well. So it's been around now for almost 3 years. I also just wanted to give a shout out to my team at Microsoft Research, who I loved working with and did such a great job on building SEAL and maintaining and releasing it. So let me mention a little bit more about this worldwide standardization community. You can go to homomorphicencryption.org. We have a steering committee consisting of about 6 of us, including myself and Kim Lina from my team at Microsoft Research. And we have planned numerous meetings around the world. So we've had 4 workshops over the last 4 years at Microsoft, MIT, University of Toronto, and Intel. And the next 2 workshops were delayed because of the pandemic, but hopefully we'll get those rescheduled. So the next one was actually the one last May, was supposed to be co-located at the UN AI for Good conference, co-hosted by EPFL and INFR and the UN IT group. And the one after that was supposed to be hosted by Samsung and Seoul National University in Korea, and that is being rescheduled most likely for this coming fall. So we will continue, and hopefully we'll get back to our in-person meetings. But the idea of creating this open community is that applications in regulated industries, they certainly require standardization, and standardization creates trust. And in order to kind of create that trust, we wanted to have as much as possible of all of the crypto technologies be open source and openly, the standards be kind of openly negotiated among academics and government and industry researchers. And in general, we've seen that open standards are highly preferred in cryptography, and unencumbered by patents and things like that, makes them easier to adopt, widely, make them available for widespread adoption. So I will say one other thing about the timeline, and that is that, I've been working in cryptography for more than 20 years now, and I started out working in elliptic curve cryptography and working on standardization for elliptic curve cryptography as well. And then also other, post-quantum crypto systems such as supersingular isogeny graphs, which I proposed in 2005 along with my co-authors. And so I've seen over time that there's often a lag between when some new mathematical system is proposed and when it can be really adopted in the industry. And I've seen in practice at least a 10-year lag between when a solution, some kind of new crypto system is proposed and when you'll start to see adoption. So we're about at the 10-year point with homomorphic encryption now. You can say homomorphic encryption is roughly 10 years old, at least the schemes that we use today, and all the libraries around the world are based on those were proposed 10 years ago. So I'd say that it's fairly ripe for widespread adoption at this point. And by putting all this work into creating this standardization community, homomorphicencryption.org, we're trying to accelerate that path to widespread adoption by creating that trust. So here's another reason why I think it's fairly ripe for widespread adoption, and that is this is a kind of a rough guide to the performance improvements that we've seen over time. So I'm not going to take any time with doing a poll, but for those of you that have heard of homomorphic encryption before, I would take a bet that most likely you've heard that it's wildly impractical and unusable and not ready for adoption. And so, while that may be true for various reasons, the reason is not really performance. That's a kind of a myth. And so I'd like to debunk that a little bit. It's true that encryption always carries overhead. All the widely deployed, encryption schemes that we use for everything today in e-commerce, they introduce a huge overhead in terms of, the extra CPU, cycles needed to do encryption. That's true. I'm not saying there's no overhead, but the overhead is kind of, I would say, misunderstood. So when I first started working in this area, it was estimated by some folks, I think at IBM, that the overhead for doing homomorphic compute on homomorphically encrypted data was about 10 to the power 13. So really a lot of overhead. And that makes it, so I mean by that, if you're going to do a computation on homomorphically encrypted data, it would take you 10 to the 13th power longer than it would to do it on unencrypted data. And so in our paper in 2011, the LNV paper, where we showed how to do these practical encoding techniques and using the new schemes such as were proposed in BV 11, we were able to bring that overhead down to about 10 to the 9. So we thought that was a pretty good improvement. But still, if something is like, a billion times, worse than it would be on unencrypted data, that still doesn't sound very good. So over time, so what you see in this graph here is that 2011, you see this is a log scale of the improvement in the overhead over time. So in 2011, you see that the overhead was about 10 to the 9. And through all kinds of improvements over the last 10 years, as of a couple of years ago, we had brought that overhead down to around 10 to the 4. So 10 to the 3 or 4 is 1,000 to 10,000 times overhead. And so that's like saying if you could do something in microseconds on unencrypted data, you would be doing it in milliseconds on encrypted data. And so that's not to say there isn't a cost. There is definitely a cost. But the cost is not what it used to be. And those improvements were everything from better schemes, better underlying schemes, to optimized algorithms for the kind of mathematical operations, the polynomial arithmetic, all kinds of tricks that have been used, to all kinds of software improvements. And finally, the last stage of the kind of acceleration is relying on hardware acceleration. So there's been all kinds of work done on accelerating further using GPUs and FPGAs and native hardware like ASICs, which is being funded now and investigated in a DARPA DPRIVE program. So there's a good possibility that the overhead will be brought down to using, hardware solutions, something like, 2 orders of magnitude. So something like 100 times worse than doing a computation on encrypted data. So I'll get to some of the other challenges that are not performance a little bit later. So what I wanted to do is kind of go back to what the applications are of this of these techniques. Unless anybody had any questions they wanted to ask right now having to do with the libraries and the performance. Okay, so I'll just go forward with the kind of application. So homomorphic encryption, as I said at the beginning, it allows you to encrypt data so that it can be computed on in encrypted form without decrypting. That's what the tool is. Now that it's, you know, a hammer, what nails can we hit with that hammer? So the fact is that homomorphic encryption does not solve all privacy problems. There's lots of different things that you might want to do depending on what industry you're in or what particular problem you're trying to solve. There's a lot of privacy problems that are not at all solved by using homomorphic encryption. And today, homomorphic encryption is most suitable, you know, and safest and easiest to use and deploy if we talk about what we call single key homomorphic encryption. That means a single party encrypts their data, and then in the end, the result is essentially decrypted by that party or decrypted by that party for someone else without, you know, any kind of multi-party interaction with someone who has to encrypt their data in using a separate key. So multi-key homomorphic encryption is possible. It's a lot less efficient, and there are a lot of other kinds of risks to be thought about. And single key homomorphic encryption can be used to enable interaction. So one party would simply have unencrypted data that they put into a protocol, and the other party would put encrypted data. And encrypted and unencrypted data can be combined, and they give you an encrypted result. And so the party who encrypted their data has the key, and they can use that key to decrypt the data. So it does allow for some interaction, but I hope you could see that it's a very simple format for interaction. And often we use a kind of an honest but curious trust model, which is saying that, for example, a cloud provider or some company that might be providing a solution would be, if you gave them all your data in the clear, they might be interested in looking at it, but they're not going to intentionally mess up the protocol that you're supposed to deploy for some kind of solution. So they will honestly kind of you know, follow whatever protocol, and to the best of their ability, they'll execute protocols correctly without, you know, injecting malicious garbage and things like that. So we can't, you know, protect against, you know, denial of service attacks or things like that with homomorphic encryption. But if you have the honest but curious model, there's a lot of different protocols that can be deployed to solve the problems that I've listed here. So for example, private outsourced storage and computation is a perfect fit for homomorphic encryption. So if you want to store things in the cloud long-term and you want it to be private, but you still want it to be, you know, searchable or to be able to do predictions or business analytics, then homomorphic encryption is perfect for that. So an example of that is like private AI prediction services, hosted private training, so uploading a bunch of sensitive data in encrypted form and creating, you know, trained models in encrypted form. That's also possible. The private set intersection allows for different sensitive data sets to be, you know, intersected, and what is returned is only the members that are in the intersection of two sets. And that's kind of an example of some secure collaborative computation that's possible. And the markets that I've seen where these techniques could be really useful are everything from healthcare and pharma to financial, government, insurance, auto, manufacturing, oil and gas, lots and lots of different applications. And in particular, just to give you a few examples, like in finance, you could do fraud detection, automated claims processing, threat intelligence, data analytics. In healthcare, everything from medical diagnosis to healthcare bots, preventative care, data analytics. And in manufacturing, things like predictive maintenance or data analytics. So these are some of the kinds of tasks that could be done privately using homomorphic encryption. So I was going to take just a couple more minutes and So I'm going to just very briefly say that over time, I've showed a lot of demos, live demos of different kinds of tasks, AI tasks that can be done on encrypted data. And these demos were all built by my team at Microsoft Research, so I'm not showing them anymore. There's actually videos and a lot of different talks that I've given. There's videos of these demos available for you to watch. And I always like to show demos because it shows you the technology in action, and it's fun to see, you know, the compute being done on a server that, you know, it returns the result very quickly, you know, much quicker than you probably think it would. But I'm not showing those demos here today. Like I said, you can watch, you know, videos of them that I've done in the past. But you should see from this list, going back over the last 7 years, everything from medical predictions such as, you know, heart attack risk to genomic predictions, you know, pneumonia mortality risk, to, you know, text analysis, so natural language processing, Twitter sentiment analysis on, you know, encrypted tweets, to image classification, cat and dog image classification, to a private fitness app, to chest ray, X-ray diagnostics, all the way up to secure weather predictions. So it's a whole range of different types of tasks that we've already shown are very practical from a performance point of view to do on homomorphically encrypted data. So hopefully that will help to dispel the myth that homomorphic encryption is not practical. And two more things I just want to talk about, two kind of success stories that were actually released while I was still at Microsoft and are publicly available. One is an Azure ML private prediction notebook. So released about a year ago and announced at the MS Build conference, it allows you to deploy an image classification model for encrypted inferencing in an Azure container instance using Microsoft Seal, and you can access the tutorial and documentation at these links. So this is what the public-facing page looks like. And then this year in January, it was announced a password breach detection feature for Edge, which is safeguarding passwords in Microsoft Edge. And I'm not going to go into the details, but you can access this through the link that I've provided here. So I'd just like to mention that, just to be transparent, it's not like all problems are solved for homomorphic encryption. So where I see the ongoing research and continuing challenges are, number one, are, you know, improvements to the machine learning on encrypted data. So both training, which we first proposed actually in 2012 with Grapel, Narig, and myself, and also improvements to prediction, such as improving the techniques introduced in the CryptoNets paper in 2016, and many other different types of ML models and tasks. So there's a lot of ongoing research. I actually have a slide. This is a bit dated from a couple of years ago, but it shows some of the ongoing, you know, research projects from different teams around the world. I'm not going to go over the details right now, but so there's continuing research in that direction to improve things. And then secondly, I mentioned already, there's a lot of work going on to continue the hardware acceleration for these techniques. And so then finally, I'd like to say that one of my biggest concerns is the kind of storage overhead and energy costs that are introduced by doing encrypted compute. I think we already need to be thinking about the huge energy costs of training large, you know, deep neural nets. And so I think that the energy costs involved in adding additional compute in order to handle encrypted ciphertext is significant, and that we need to think about that kind of thing. So those are the kinds of challenges that are on my mind. I wanted to leave you with these resources. These are, you know, external products that have been built. As I said, Microsoft Seal is been released to open source. 10 Seal, Pi Seal, and TF Seal have all been released. They're all available on GitHub to use Seal for anything from TensorFlow to other types of operations. And so I think I will end there. I just have about 5 minutes left for questions, but hopefully I've answered some of your questions or thoughts on this matter. So thank you so much.
Thank you. This is very fascinating, Kristen. This is Edmund Martin, one of the hosts on this meeting. There's one question from Ulibas Amour, which is a two-part question. It says, which machine learning algorithms are FHE friendly? And this question number 2 is, what are the changes to train machine learning algorithms in FHE? Why most of the work make assumptions that the model is trained on clear data?
Oh, great. Thank you for the questions. So let's start with question number 1. So, and in fact, in our 2012 paper, which is actually almost 10 years ago now, we defined a concept which we called polynomial machine learning. So meaning what the FHE friendly algorithms are any kind of compute that you basically describe with polynomials, where the polynomials are not of very high degree. So if you translate that into the language of circuits, that means low depth circuits. Now, you might say, well, deep learning, that's not low depth, and you're right. So the way that we do, for example, deep learning is approximating deep learning networks, basically with shallow networks that are much wider, because those are much more FHE friendly. And in general, this has opened up a new direction of research in machine learning, which is approximating machine learning algorithms with low depth polynomials. So I could go more into detail, but that's really the answer to your question. Which ones are HE friendly? They are the ones that are low depth circuits. Right. And also that's also the reason why I never use the F for FHE. F is fully. It was originally meant to refer to the fact that you could do both addition and multiplication like any type of circuit. But there's a lot of confusion between, like if you say PHE, I see someone else in the comments said PHE like partially, or they used to say somewhat homomorphic. So S or SWHE. So just to avoid all of that confusion, I just say HE. HE refers to, for me, refers to being able to do two operations, addition and multiplication, or general and or circuits. But the question is, what depth do you want to allow? So do you set up your system so that it can allow for arbitrary depth, which is usually what's meant by FHE? Or do you decide what depth you want ahead of time, which could be arbitrarily large? It's just that you've decided it ahead of time, and then you actually tune your parameters to allow for that computation. And so in that sense, you could still say it's fully, but in fact, it's not, and that it can't be. You can't change it later if you haven't set up your parameters to allow for arbitrary compute. But it's much more practical if you decide ahead of time how deep you want to be. Okay, so sorry for that second half of my answer to your question. Probably made it a little too complicated, but.
Yeah. Well, thank you. We have time for one more question, which is, what do you think about the homomorphic encryption impact on GDPR and HIPAA and other regulatory compliance topics?
Oh, that's a really good question. So okay, so first of all, I'm not a policy expert, so I can't really, comment, and I can't comment in my official, capacity in working for Facebook or, having worked for Microsoft. But from a kind of a common sense point of view, here's what I know. Unfortunately, just encrypting data doesn't currently help you to comply with regulatory requirements, because most legal, systems around the world don't recognize encryption as having some kind of different status. So it doesn't really help you to comply with, HIPAA or other regulations, even GDPR to my knowledge, to encrypt the data, unfortunately. I hope that will change in the future, and that industry will lead by deploying encrypted solutions to protect privacy, and regulations will catch up with it. But that's just my own, personal viewpoint.
Fantastic. Well, thank you, Kristen, for this wonderful presentation. It was at some points mind-blowing, but we got through it. Very informative, and thanks again for your time. I will just add to the audience, thank you for joining us. This is our monthly meeting. We meet at the fourth Wednesday of every month. And if you like the presentation and the other talks that we bring to this audience, consider supporting OWASP Foundation at only $50 a year. And if you're a student, it's only $20 a year. So, and with that, I'll close the call. And thanks again, everyone, for joining. I know everyone's busy and hope you enjoyed the call.
Thank you. Have a good day.
Bye-bye.
Bye.